guess we did, I went through this one. All right, so let's take a look at a graph. Somebody on your engineering team, they're like, hey, look, did this linear regression. My R squared is something, so therefore it worked. When you look at this, there's like a dotted line that's just called linear regression. And then there's a whole bunch of dots of like the land temperature anomaly. What do we get out of this information? Or what do you get? What do you think? And I'm skipping everything that we did, all the work that we did to get here, just to see like what was the point? Why do this to begin with? What is this graph showing? Okay, here, yeah, all right. Yeah, it's just called like anomaly. Okay, average. So take total average. Oh, moving average. All right. All right. Yeah. What do you think? Okay, yeah. That's all right. But if you look like if someone showed you this, does it tell you? Okay, so there's something, temperature and time is connected. Yeah, there's a measured, yeah. Okay, yeah. Yeah, definitely trend. Yeah. For someone showing this a lot, what's that? But it is linear. Well, okay. So you think you trust that it is linear? So we can draw that straight line. Yeah. And would be, they would continue predicting. Yeah. Temperature anomalies.
It looks like it would.
You think it would?
Right, because everything that all the points are across the
Yeah, like it seems like slow is changing, right? Okay.
Shows up.
All right. All right, so the things that we kind of noticed, even just a quick glance, it's like temperature, time has some functional relationship, and then we started to question, like, is it a linear relationship? And if we do a straight line fit, then all we can do is find a straight line to go right through it, right? Like, we can do other fits, but if you say temperature time is linear, then you will find a line that is the best linear line to go through it. But roughly, we could kind of see like this versus here. I mean, this slope and that slope kind of look different. Like, it seems like there's something different there. Maybe if you're getting like real fancy, maybe it's some kind of polynomial equation, right? Like but it seems like there's something other than just every year there's an average increase in whatever this land anomaly is. We didn't even discuss like what that means to you. But in the reading, there's like the data has a source, this data. Coming back up. Skip past all the math. So this National Ocean and Atmospheric Administration, which hopefully, is it still there? Okay. Like, as I realized, so there's a lot of government websites with like good data being taken down. So as I was clicking on this link, I was wondering, is evidence of global warming still available from the government? Which is, pardon my French, but a fucked up thing to have to wonder about. But it seems like it is here. For now, yeah. So get in there, create an anarchy, like copy it yourself. Here we have the data in a little Jupyter notebook, so at least we have like some history there. Let's see. Yeah, I'm trying to find if they still have a description of temperature anomalies, because here's average temperature. There's max, but where's the temperature anomaly? I don't know. All right, anyway, sorry, that was just a side thing that I just realized, like, do we have access to this? We have access to it. It's saved in a little CSV file for us. Global land temperature anomaly. Globe. There we go, temperature anomalies. And here's the average temperature anomaly. So yeah, if you wanted, you could actually increase the time, like look into the future a little bit further, since this data set just goes up to the year 2016. You could look out into the future. We did not reverse the trend yet. It's still a work in progress. And one So one way, like if you think there is a change, one way is just split the data and say, at a given point, there's a change in slope. So let me do another best fit that way. And here, comparing, here, we can compare them, put them side by side, right? Or at least top and bottom. So which one, like looking at these two plots, which one would you say like a better like slope calculation? The second one? Yeah. I mean, I would agree. Like it looks like this one has one trend and this one has another trend. And you can, like, there's the problem of overfitting. Like we could split this data set up into every 2 years, fit a straight line. And now every line is exactly matching the data, but we get a lot of noise there. And then some people might question, like, should we have split it at this year, 1960 or 1970, or should it have been like 1980? It's like, well, you can try that, see what the difference is. One way you could try to figure it out is like find the R-squared value for like 1970, 71, 72, 73, and look for a minimum R-squared, because R-squared is some measure of this data. If we look at this data, the range, do you know what R-squared is? Does anyone know? Like I know you've done some stats, some people have done like sensors and data, applied measurements. Do you know what an R-squared value does, what it's telling you? It's, a lot of people call it like the goodness of fit, but you can have a very low R-squared with a very bad fit. So it's, and okay, yeah, so the variation of the data versus the variation of your model, kind of like that. So like in this case, if I think of the variation as just the max minus min, which is not exactly what we use standard deviation to describe R-squared, but you could use range. Like what is the range of data without your model? And it's 2 degrees. Versus if I look at what is the biggest distance, here, this is kind of like the lowest from my line and the highest from my line. So this is about half a degree and that one's about 1 degree. Is like 1.5 degrees. So we reduce the variation by half a degree because we said it's a straight line. And that seems reasonable. Versus here, maybe this is my max. And maybe somewhere over here is my min. Now the range is more like 1/4 of a degree because we said it's 2 lines. And this is where the goodness of fit is not like a great thing, because if I draw the line exactly through every single data point, then my goodness of fit is 100%. I'm exactly fit to the actual data, but I'm overfit. So that's like hand wave, without getting into the math of like, how does it work? R-squared is telling you like how much did you reduce the variation in your data by saying it's actually a straight line. That's some kind of function. Anyway, all the questions that you didn't ask, here are all the answers to. Cool. What else are we working on? Working through, just plugging along. Yes. So that's slow. One of those. I think they use GPUs to process something. There's some kind of graphical processor. Parallelize something, take in some kind of information. I guess that's how that was the that one still has causes, right? Like if you, yeah, if you know how it's being generated, then you can predict what numbers are coming. Yeah. So you're in the code. You're like slowly into the focus. Randomness is not possible. Yeah. It might not be. Yeah.
Yeah, so I have Amazon download those by having it. So I'll just tell you.
Yeah, so in this website, like you have your own computer.
Yeah.
It's,
But how do you know what files are on these programs?
oh, you can
If you choose it,
if you put
I used to play that.
and I always believe so.
and you can see all the files in the current folder if you pick that blue folder. Now you have like everything from
So like you were.
yeah, I
CSV, that's all I can.
so if you so that dot means go from one folder and then it's where all of our data is stored.
So we don't need it.
No,
Okay.
you can upload pictures. Graph files into that server. Oh, yeah. Oh, yeah. Sure. Yeah. That's not part of it.
There's no way. I remember showing us a bathroom. I was like, is that now?
The reason I saw their shadow through the window.
We're determined about
Dude, I had to stop
stuff.
so bad. I'm not gonna lie. I saved the beer though.
So I'm like not surprised.
Are you saying because it is an assignment?
Literally just full body fold over the turnstile. Yeah. Yes, like it was done every time. Lamar doesn't run to all 5 coast guards until it switches over to the I thought that was gonna be like the freeze at all time. Dude, every time I call him, he's like, I'm down in for food. No, but the next week he'll go up like 1,200. He's like, I did it for that whole time. I'm like, why? So for project 2, it's just answer these questions like just right there, and then these next steps. The first part is all like an example.
Yeah, so the goal is like run our own analysis and answer process ideas or explain. Well, yeah, shortcomings,
Why it's good.
possibilities, yeah. Yeah. Like if you think it's a bad model, find what are the metrics. Or
Yeah, that's right.
yeah. That's a strong man.
Can't trust anybody.
Yeah, that's a strong man. The actual model.
The
core. Yeah. What's the core?
If you were Brian, maybe.
Brian, maybe. Yeah. Huh? Where did my mouse go? Why can't I click? There we go. Lost my clicking ability for a second. All right, so some people were taking a look at like Monte Carlo methods. So just quick and dirty Monte Carlo intro. The computer can generate pseudo-random numbers. They're not completely random, so you can't use them to like generate passwords or something. Like it is something. It has a traceable way. Someone could reverse engineer like what random numbers they are, but they're random enough for Monte Carlo predictions, where Monte Carlo depends on like if you have random numbers, you can start making calculations. So it's used all over the place for like reliability measurement. Like if you have a process, some kind of manufacturing process, and you know the probability of failure in like multiple steps, you could use Monte Carlo to figure out like, all right, how do I propagate that through the entire assembly, things like that. US Coast Guard uses it for like rescue mission. Radiation is another big one because like nuclear energy looks kind of random. Like there's probability fields of like where particles will end up based on quantum mechanics. So that's like known field of where they might be. Then you can use Monte Carlo to say like, all right, here, if they're going to be in this sphere of influence, where do they all end up? So all sorts of cool stuff. We'll do some financial modeling with like a random walk in the project. And then I was saying before that if you do Monte Carlo method, like if you say you know Monte Carlo or you say that you've used it before, there's just a standard rule. You have to calculate pi. It's like the very first thing that every single Monte Carlo lesson starts with. So I don't make the rules, but we'll follow them. We'll follow suit. And I think part of it is that it's like a nice visual representation of like if you're throwing darts at a dartboard and you're not very good at it, like you can randomly get the board, but you can't actually get a bullseye with any accuracy, then you'd end up with like some kind of pattern like this. All the green dots, the ratio of like how many green dots there are to how many red dots there are, that's got to be related to the area between the square and the circle. And that's kind of what we're doing. It's like pi r squared versus 4r squared. That's always a pi over 4. So if we have enough random locations, they should converge to pi over 4. And so I turned it into like a function where I'm generating a random x and a random y based on some n, however many spots I want to create. Each of these are independently random. So x is going to create a different number than y. And that's part of the key. You can't say like, just give me an x, y that are both the same random number, because then it would just create a straight line. Find the radius, square root x squared plus y squared. Number in the circle. If r is less than 1, it's in the circle. And total number of points, they're all within the square. So the square area is based on like total number of points. And what I can see is that for 1,000, if I use 1,000, n equals 1,000, I'll run it 10 times to try to get like how accurate is it in each time. I get 3.17, and the actual pi is 3.1415, at least from our computer, the best that our computer can store that value of pi. If I want to reduce this standard deviation, increase n. So the bigger n gets, the more converged your Monte Carlo is. And that's kind of the magic here. That's always the answer for Monte Carlo, is like just increase the number of times that you run it. So if I increase the number of times that I run it, it's still going to have the same standard deviation. Roughly the same standard deviation. Maybe my pi is a little closer, but it's still, each run was not as accurate. So instead, let's run 10 times, but instead of 1,000, we'll say 1,000,000. No, is that 1,000,000 yet? 1,000,000. And then it'll think about it for a second as it runs through generating all those numbers. Is that too much to ask? Maybe. On a Wednesday, on a rainy Wednesday morning. There we go. 3.14047. Standard deviation 0.001, which makes sense because by time I get to the digit that's off, it's in that third decimal place. So that's it. Yeah, if you run through these, you've done Monte Carlo to calculate pi. We'll use another method in the homework, and we can talk about that another time. Nothing else. As we're coming into the end, plan for Friday was take the hour for this block, work on your own, and then Monday come back questions. So no meeting here, at least in person, for Friday. You can post questions on Husky CT, discussions are open, or yeah, that one, that's the best place to ask questions, so then everyone can kind of benefit from answer. I don't ignore emails, but it's nice to have like, oh, because if one person has the question, then at least 10 people have it. So it's nice to have like a resource for our class. Cool. All right. Then I'll see you on Monday.